Thank you for joining this session. So today I will speak about evaluating H2 infrastructure need in a power, gas, and hydrogen regional model. Just to present very briefly, I'm Diane Delacaise. I'm a team leader for multi-energy models within Engie global markets. Today's objective is to present actually how did we use Plexos, a Plexos model that we developed that covers different energy vectors with a long-term horizon, which is 2050. And how do we use actually this model to evaluate what is the need for hydrogen infrastructure? And I will explain first actually what is the context, the overall context for this study that we did with my team. Then the methodology that is I would say the most important part of this session, because here we are all more or less Plexos users. So we leverage basically on Plexos capabilities to model this multi-energy system. And then I will present some key results of the study on both the optimal hydrogen production mix and also on the need for hydrogen infrastructure. And then conclude, and hopefully we'll have some interesting Q&A session. First of all, let's start with the context for this study that we did with my team. So in April 2025, the French hydrogen strategy was published. So it's an updated hydrogen strategy, which focuses mostly, I would say, on the local production of hydrogen with electrolysis. The strategy, despite being somehow a long-term strategy, the main focus is really for I would say the 2035 horizon, but it still gives some hints on the long term of hydrogen in France. As I said, the focus of this hydrogen strategy was really on the local production of decarbonized hydrogen, using electrolysis with grid connection, given that the French power system is mostly dominated by nuclear power. So this hydrogen is considered as green hydrogen. We have some objectives in terms of hydrogen capacity that were set. So 4.5 gigawatt up to 8 gigawatt by 2030 and 2035. In this hydrogen strategy, the hydrogen was really considered as a decarbonization option for mostly industry and also some transport segment. And in terms of, I would say, infrastructure, it focuses really on the development of hydrogen hubs in major industrial zones or ports. From, I would say, a mid-term perspective, the strategy really says that hydrogen production will be close to consumption sites, and mostly industrial hubs, so the Chemistry Valley, also in the north of France, in the region of Dunkirk. For the longer term, it is said that a European hydrogen backbone could emerge with transport infrastructure between hubs. However, the strategy is really not focusing a lot, I would say, on infrastructure development and on the need for this infrastructure to be developed. In particular, it was just written that the development of a transport network between hubs could be analyzed under the condition of its financing by the potential users. So somehow it was not very, I would say, very pushy. Hydrogen storage is also mentioned as a way really to unlock the flexibility of electrolyzers. And this development is foreseen in the midterm. As you can see, just very quickly here, the strategy was not, I would say yes, not very prescriptive in terms of infrastructure development. So there is really a need for us, I would say, as an infrastructure developer, to somehow challenge also this hydrogen strategy with techno-economic analysis. So the idea was, in this study, to develop first a regional view of hydrogen production and on the optimal mix. So should we focus really only on green hydrogen? What is the role of imports? What's the role of blue hydrogen? And also assess the need, the economic need of hydrogen infrastructure. So both transport and storage. So in the study, the key questions that we addressed were first, what is the optimal production mix? Should we focus only on green hydrogen, or is there any room for blue hydrogen? The optimal location of hydrogen production. So basically the question is producing hydrogen near consumption sites the most cost-effective approach? And then, what is the economic need of hydrogen transport infrastructure? So given, well, basically the anticipated development of green hydrogen production, will a hydrogen backbone be economically efficient by more or less 2040 or 2050? This is just for the context, the questions that we aim at answering. So now, given that we are in the Xcelerate conference, I will of course discuss a bit and present what was our use of Plexos actually to model this multi-energy system and to assess the economic need of hydrogen infrastructure. So the analysis that we developed is based on, I would say, a common framework for most techno-economic analysis with different type of inputs, a Plexos model, of course, and outputs. So in terms of inputs, what we used is really the aggregated demand by energy and end users for each region of France. And just one point in terms of scope, so actually we are modeling in total 16 European countries, so which cover more or less 85% of the energy demand of Europe. But for France, we have a regional model where basically France is divided into its administrative regions, and I will come back to that later. In terms of supply, we do consider the existing power and gas generation plants, the technology cost, the fuel and CO2 prices. And in terms of infrastructure, we do model the power and gas existing infrastructure, and there is also this capability with capacity expansion to develop hydrogen infrastructure. In terms of then the core of the model is really an integrated multi-energy model, so with both power, gas, and hydrogen. It's a capacity expansion model, which means that basically the model authorizes investment in certain technology or certain assets, considering the future cost of those. And the idea of the model is really to minimize the total system cost under several constraints, such as, of course, supply and demand balance constraint, CO2 emission constraint. So here we are in a scenario that meets net zero by 2050, and we also consider power and gas and hydrogen transmission constraint. And then in terms of outcomes for the model, so of course we have the typical regionalized power, gas, and hydrogen supply mix. We have the flexibility need as well, the infrastructure development and use, and also, yes, points on storage, import and export. to be just a bit more precise in terms of modeling, so we divided basically some of the parameters between either what we call exogenous parameters, so basically those are set as input to the model, and endogenous parameters, which are really the result of the optimization. So, for instance, the short-term renewables development were based on countries' targets, while the longer-term renewables development are optimized as part of this modeling exercise. So if I focus just on endogenous parameters, so those are really the result of the linear optimization. We have, for instance, the battery development, the long-term renewables, as I said, the gas supply mix, the decarbonized thermal investment, the hydrogen infrastructure development, and the imports. While exogenous parameters were mostly on, for instance, biomethane cost, import cost, existing infrastructure for both power and gas. Now, as I said, we proposed really a spatial representation of France that is aligned with existing gas and power transmission infrastructure and transmission constraints. So what we did to come up with this regionalization, so here what you see is that basically we have grouped some of the administrative regions of France to end up with 9 regions. And this group limits somehow the model complexity while preserving the right granularity to analyze infrastructures. Now, just a very small point on some technical challenges, because here, of course, I'm giving a very, very broad overview of this modeling exercise, but still, for those who are modelers, you can see that there are some technical challenges to overcome. The first one, I would say, is the computational complexity. In this type of models with 16 European countries plus somehow 9 additional regions for France, given this wide geographical scope, there is a need to somehow limit model complexity by doing, for instance, stuff like grouping assets per technology instead of modeling individual assets. We also had to linearize unit commitment constraints. Then a second challenge is really on also the climate uncertainty. So we were not able, with our basically calculation capabilities, to do like stochastic programming. So what we do is that we modeled instead 15 climate years in a somehow deterministic model with perfect foresight. And then another one of the many challenges was really the power network representation, because as I said, here we model different regions for France, which means that somehow we have a zonal model, but that tends to be closer to a nodal model. So what we did to model actually the network constraints, the power network constraints, especially between regions, is to actually depart from a nodal model that has been developed within market analysis, so within my team, and to calculate, to extract somehow what are the available transfer capacities between regions. So those are just to give a flavor of the modeling challenges that we had during this exercise. Now let's move on to some key results on first on the optimal hydrogen production mix, which is the first point that we wanted to challenge from the French hydrogen strategy. and then discuss also the need for hydrogen infrastructure in the mid to long term. As I said before, the French hydrogen strategy really focuses on electrolysis as the main way to, well, basically to produce hydrogen. So here, the first question was, okay, what about maybe blue hydrogen? So here I just I will give first the overview of the results and then give a bit more details on that. The first point is that what we saw, and in accordance actually to the French hydrogen strategy, we observed that somehow from 2040 onwards, electrolysis really becomes the dominant pathway for local hydrogen production, and this is in line with the preference that was set by the French hydrogen strategy. And what we see is that, for instance, by 2050, so in our base case scenario, electrolysis really supplies almost half of the hydrogen need. Steam methane reforming, SMR, capacity is not deployed basically given the decarbonization constraint, and blue hydrogen remains very limited in France. And just a note, stopping there, all those results here that we present are based mostly on the base case scenario. Just for the sake of simplicity, I will not tackle all the different sensitivities that we have. The second point that we wanted to address was what is the optimal location of hydrogen production. So what we saw with this analysis is that in the near term, domestic hydrogen demand was predominantly met by local steam methane reforming and electrolysis, with a small part, I would say, of imports. We also observed that electrolyzers were located near the end users, and this is due basically to the absence, to the current absence of hydrogen transport infrastructure. And from more or less 2040 onwards, what we see also is that there is the opportunity to import cheap and clean hydrogen, especially from the Iberic Peninsula. And those imports tend to outcompete somehow, to compete with local production. And so what we see is that somehow in terms of need for infrastructure, the expansion of the hydrogen backbone, so of this transport infrastructure, proves to be cost efficient. And really the last point is that we observe somehow that this analysis shows somehow that developing a national hydrogen backbone on top of the European hydrogen backbone is economically efficient, particularly to enable flows from regions where it will be cheap and affordable to produce hydrogen, so for instance in the south of Europe, to regions with a higher hydrogen demand. Now I will be quite quick because we have only 10 minutes left. So here is just an illustration in terms of hydrogen balance. So as I said, what we see here, we display graphs for hydrogen, so both local supply and local demand, international flows, and those results in terms of equilibrium for hydrogen in the different regions of France. So, for instance, here in 2030, we see that the hydrogen balance is somehow mostly met with local production, while from 2040 and from 2040 onwards, we see that there is really a predominance of imports with the development of a backbone. We also see that in some regions there is a sort of oversupply of hydrogen production that is then transported to to neighboring regions. And also what we saw with this analysis was somehow the fact that electrolysis was also developed here to cope with power network constraints. So this is something that we don't directly see here, but that we could observe. So why basically in some regions we have such a high hydrogen supply? This is mostly for flexibility needs. Just a first illustration. Then maybe I move on directly to this one. Here we display actually the focus is more on hydrogen infrastructure and flows. So just to give a first point, as I said, the hydrogen infrastructure development is a result of the optimization. So what it means precisely is that we set possible routes for the development of the hydrogen backbone in France. And the choice of investing in those routes is a result of the modeling exercise. So what we saw, and here this is only one of the many, I would say, many scenarios that are possible. So it doesn't represent actually, just a caveat. It doesn't represent like the strategic Engie view. In case you want to sue me afterwards. So here, what is interesting actually in this here is that basically in the short term, somehow we have very limited import capacities, especially from Spain and Portugal. And that what we saw somehow in this scenario is that we would have mostly like potential flows actually from Germany to the eastern part of France. In 2040, maybe more interesting, we see that there is first transport routes that develop and that enable to import hydrogen from low production cost countries such as Spain, and we see that somehow two corridors are developed. So one, from south to north, both, and one in the western part, one in the eastern part of France. It's interesting also to see that the hydrogen backbone, so the plan that is made by the EHB, proposes somehow a very circular network. So actually in the hydrogen backbone, on top of those routes, you have also routes that go from east to west, and both in the south part of France and in the north part of France. So here in the analysis, what we show, and this was the case in most scenarios, is that somehow this circular backbone was not necessarily cost efficient to be deployed. And then the last point is for the very long term, and I deliberately show this result because it can be, I would say, a bit surprising, and it can be criticized as well. Is that, as you see here, in the longer term, we don't really see we don't have anymore this link between the region Occitanie and Provence-Alpes-Côte d'Azur and the Grand Est, so in the northeast of France. And this was basically one of the results. So in this scenario, and we are actually challenging this because, of course, the development of an infrastructure is not done only for to be used for only 10 years. What we observed also is that from a modeling perspective, we had bidirectional flows. And this can be also challenged, and there is also a technical challenge in terms of how is the flexibility of transport infrastructure used. Since we have only a few minutes left, I will just conclude quite more generally, actually, with this model. First of all, the Plexos software was really key, actually, for the development of this type of study. The fact that we have the possibility to model both power, gas, and hydrogen enables really to highlight the benefits of multi-energy sector coupling. The development of this regionalized view was also really key in the sense that it enables to assess the system benefits of locating specific assets in certain regions, so reflecting also the local congestions for both power and gas. Something that I didn't show here, but the multi-climate year modeling also enables to evaluate the asset-specific risks depending on climate conditions. The fact that in extreme weather years you have maybe more need for flexibility. So this is something that we were able also to assess. And the infrastructure modeling that we used here with the capacity expansion was also key to enable to assess really the economic need for key infrastructure. So here, hydrogen transport, hydrogen storage as well. And I will stop here just to keep some time for a few questions if there are.
Hi, Ali Akeri from Agri. Just three questions. The first one, how you forecasted the hydrogen prices as an input into your model? And the first one, where these power comes from to electrolyzers? Is it dedicated power or is from excess power in your model? So how you describe into the model, so to when generate hydrogen, is there any constraints? Is it coming from dedicated power or is coming from excess power system? Yeah. And finally, just I wanted to ask about like seasonal storage, how you model in Plexos the seasonal storage of hydrogen, and what technology you have considered. I'm not sure that you remember all these questions, just the first.
I will try.
Thanks.
So thank you for your question. So the first question is, if I reformulate, was what is the hydrogen price? So this question is, we don't set a hydrogen price. So the hydrogen price is actually rather a result of the optimization with the equilibrium of supply and demand. Then the second question was on the when are electrolyzers functioning? So this is also a result of the optimization. So I maybe didn't mention, but the model is a model with hourly granularity. So basically we model electrolyzers with their flexibility constraints, so somehow ramp up, ramp down, and also the investment cost needed, because electrolyzers are also a result of the optimization. Yeah, so somehow, and the electrolyzers are connected to the grid. So indeed, we disregard somehow like RFNBO constraints, assuming somehow that with an ex post calculation we can see that these RFNBO constraints are met because the power mix is mostly decarbonized. And then the last question was on the use of storage. So here again, the storage are modeled with using actually the Plexos capability for modeling storage with injection and withdrawal constraints. And we indeed observed that hydrogen storage, so where we have salt caverns actually, was providing seasonal flexibility. And I see that we run out of time. Thank you.